Okay. All right, we're going to get started with the first talk, and I'll be telling you about developing with large language models. So, as you probably have ascertained by now, this is a topic that I've been really interested in over the past year. I and my team have been really digging into this. We've found some really exciting new techniques and findings in how we can leverage LLMs for development. And I wanted to talk to you kind of about lessons learned and about how we use it and see if it could be leveraged for you, whether you're excited to use it or just kind of curious and want to keep up with the technology and understand what the developments are. Whether you're for or against it, I think it's good for you to understand what people are doing. So this is kind of my attempt to be at the cutting edge of this technology, though it is changing incredibly rapidly. So keeping up with this has been basically a full-time job. But essentially, the critical point here is that we've reached a critical point in AI. Okay, so and we're to the point where there's rapid development in two key areas. One is that the LLMs are getting smarter. So by the way, LLM stands for large language model. ChatGPT is a large language model. There are others. It's really not the only game in town, though it is the most famous. But actually, I have been experimenting with others, and I actually would recommend others for a lot of use cases. So those LLMs are getting better and better, including OpenAI's models, also many other companies. But also at the same time, the surrounding tools around those models are getting better and better. And the capabilities of these models are really dictated by both the intelligence of the models themselves and the capabilities of the tools around them. And I've come to believe through this exploration of these LLMs and the tools around them that maximizing our impact as neuroscientists means becoming experts in these tools. And in two really key ways. One is using these tools to accelerate our development. They have an enormous potential to allow us to write better and faster code to analyze data. And then the second is building tools to facilitate scientific discovery. And really, ideally, let me get out of the way here, you'd be doing both at the same time. You would be building tools to facilitate scientific discovery, and while doing so, using those same AI tools to develop that software. Okay. All right. So a little brief history of the recent developments. Now, this plot at this point is actually a little bit old. But on the y-axis here is the MMLU, which is a benchmark where basically there are like thousands of questions in domain-specific areas, just like multiple choice questions. And the y-axis, the x-axis is time, and the red are closed source models. The green are open weight models. And what you can see here is that the models are getting better over time, essentially. That's number one. And number two, the point is that the open-weighted models are catching up to the closed-source models. And that trend has been continuing since this plot was made. This is showing Claude 3.5. Since then, there's been Claude 3.7 and Claude 4.0, and both of them have pushed the limit of this benchmark and many other benchmarks. Now let's look at how much these models cost. So here on the x-axis again is time. The y-axis is the cost per million tokens. And what we're looking at is each of these colors here represents some threshold of intelligence as measured by performance on this MMLU. Now, this is one of many benchmarks, but this is just one proxy for intelligence. So, or at least capabilities, if you don't want to use the word intelligence. So here's a moderately capable model that knows something about the world, but really is not an expert. And a score of at least 83 is like a really quite knowledgeable model that can answer many questions and can be useful in pretty advanced questions. So here, this is a logarithmic scale of cost per million tokens. So you can see that the trend line is showing roughly a decrease of 10x every year for the same score of model for purple. And then that trend is continuing for orange. So basically, yeah, Jake.
That's the cost to use it. Does that also correlate with the cost of the energy usage and things on the back end providing?
So the question was about the energy usage, is that whether that correlates with the cost. I would naively assume that it would correlate, though, there's always like, venture capital money going into it. I mean, I imagine there's kind of some like Uber situation going on where like the cost is subsidized by venture capital funding, and we're not really always paying the true cost of these things. So who knows, really? But presumably that will level out to the point where the cost will be roughly proportional to the energy usage. I think we're just kind of in like murky territory right now as things are getting started. This is Jake, by the way. This is the guy that I mentioned who's the developer, one of the developers of Ketalysort 4. So anyone who's interested in spike sorting, this is a really great opportunity to learn about state-of-the-art spike sorting. Okay. So this MMLU benchmark, it's one of many, and it may not be the most relevant for coding or science even, really. So it's just kind of general domain knowledge, but it's not like science-specific knowledge. So, one other benchmark that it might be more relevant is this software engineering bench. Can LLMs solve real-world GitHub issues? So here are a collection of real issues in the scientific Python stack that have been identified as tasks that have a clear solution, and you can propose it to an LLM and see if they can answer it, right? So this is an attempt to really take this abstract idea of intelligence or capability and really like nail it down to really very specific things. So this is one of the really cool benchmarks that really gets at like how useful are these models. And there have been like really impressive results. The results have been climbing every year, and right now, Claude Sonnet 4 can do 72.7% of these without any help from an external developer. And that might seem a little wild to you, but I will show you some demos later to make that a little more believable. But yeah, they're actually, I wanted to go far enough down the list to get to the first open source model, which currently is DeepSeek R1. Though there's been a lot of development lately in open source models, and I expect that to change very soon. Kimi K2 was just released, and they haven't released a reasoning mode yet, but I expect that to be somewhere in the middle here.
You're probably going into these, but I'm curious, when they work on these issues, are they just scraping the web and have access to the repository? Is there a way to integrate the whole repository in the prompt?
Yeah.
Or are they just...
Yeah, I'll go into like how all of this works. Yeah, but that's a good question. Like, how exactly does this work, right? Yeah. Another really good benchmark is the Aider Polyglot benchmark. So they basically took like exercises, like educational exercises in Python, and they were like, well, can the AI do these educational exercises? And here it's nice. So they have a bit of information about how they've done these exercises, where they have unit tests to make sure that the code actually does the right solution, and they provide instructions and presumably context. And they've found the nice thing about this leaderboard here is it shows you the performance, and it also shows you the cost. So you can see here this O3 Pro has the highest performance, but it's also way more expensive than most of the other models. So you can get almost as good performance with Gemini 2.5, the Google LLM, the latest Google LLM, for a third of the cost, right? So that is good to know. But of course, these are expected to decrease pretty rapidly. We're going to get models that are cheaper and cheaper. And then finally, so the issue with both of these is that they're gameable, essentially, right? Like you can tailor your LLM to be really good at specifically these exercises. Even if you don't feed it exactly these, you can just kind of use a training gradient that like gets the models to be better and better at these specific exercises. So it's not necessarily clear if this is going to generalize, which is why I really like the LM arena. So how this works is any user, you all could go to this website, give a prompt, and this particular one is all about web design. Is this like shaking? Okay. This particular one is all about web design. So you give it a prompt like, hey, you design a dashboard for picking stocks or something like that. And then 2 models go head to head trying to answer this prompt. And you are blind to which models are which. And you just pick which one you like. You can say left, right, or tie. And then from that, you can use ELO scoring, which is the same scoring system that they use in chess, to rank all of these different models against each other. And the really cool thing about this is it's very difficult to game, I guess, unless you had like an army of people proposing and then you kind of knew the signatures of your model. I suppose it's possible to game, but you couldn't simply use a training gradient because you don't know what is going to be in the future, right? So, so that's why this model is like, this benchmark is so interesting. And there are a bunch of these arena type things. I'm just showing one of them. Interestingly here, Gemini 2.5 Pro comes out in the lead, followed by DeepSeek R1, which was actually pretty low on the previous test. So we're getting basically some mixed results, like sometimes Sonnet's in the lead, which is Anthropic's LLM, sometimes Google's Gemini is in the lead, sometimes OpenAI's models are in the lead. So I guess that the takeaway message here is it's worth understanding the strengths of these different models and trying multiple different models, but all of these different companies are creating very strong models that are competitive in these coding tasks. I would like to note that DeepSeek, the open source DeepSeek, is doing surprisingly well here, which is really exciting. Okay, so how do you actually use these models in coding? So I like to think about it as like 3 levels of sophistication. So the first level is as a chatbot. And I think probably all of you are familiar with using LLMs at this point as a chatbot. And you already know that you can ask it for like, oh, we'll give you the regular expression for this, and it'll just print out the answer. Or you can say, hey, I'm getting this bug, and it will give you some advice for how to fix it. Or even it can give you like architectural advice about how to design something. It's actually quite powerful as a chatbot. And so there's a lot you can do as a chatbot, not just in programming, but in all sorts of domains. So it's certainly a great way to interact with these LLMs. But it's, from a software development perspective, there are much more sophisticated ways of working with them. The second most sophisticated would be autocomplete. So this is like using Copilot is the most popular, well-known example of this, where I mean, we've had autocomplete in your interactive coding environments for many years, and this just kind of takes that and takes it to the next level, where you can start writing a function and maybe you comment what you're trying to write, and it just autocompletes the entire function for you. Can I get a show of hands who's tried like LLM-based autocomplete methods? Only about half. Interesting. Well, I recommend giving it a shot. Copilot's really strong, and you can install it as an extension in VS Code. And there are also open source, open weight options if you're kind of philosophically more inclined to do that. Of course, you have to be careful. It's not 100% right all the time, but it's gotten really good at, you just edit code, and even now, it just doesn't even always recommend things right where your cursor is. It'll recommend a change anywhere in that file. So if you change a variable name, for instance, it'll suggest that, oh, maybe you want to change that same variable all over the document, like that kind of thing. So definitely check that out. But I'm actually not going to talk about that. I'm going to talk about the third level of sophistication, which is coding agents. Okay, so a coding agent it facilitates automatic communication between the coding interface, such as your IDE or your command line, and an LLM. So basically, instead of in a chatbot, the workflow is you have your code, you copy it, or your error, you copy it, you paste it into the chatbot, you read the chatbot's response, maybe it produces some code, you copy that code, you paste it into your IDE, you run it, you copy, you paste. There's a lot of copy pasting, right? There's a lot of manual steps here. So the question is, can we build a tool that automates all of that for you? That's essentially what these agents are doing. And it has certain abilities that are provided to the LLM. So the LLM is instructed, hey, you have these tools you can call. Now the LLM, at the end of the day, all it's really doing is producing text, right? We know LLMs, the way they work is they're just predicting the next character, right? So they don't literally have access to tools. But you can tell it, oh, if you produce text in this exact syntax, what we'll do is parse that text and know how to call the tool, right? So it'll give you function calls. And so those function calls can allow you to do basically anything, right? You can list directory trees, read files, edit files, run commands in the terminal, read the output, and then you can, I'll talk a little bit about creating custom tools with MCPs, which are model context protocols. This essentially, you can think of it a lot like a REST API. It's basically a protocol for exposing tools to an LLM. And there are lots of examples of this. Every week a new type of agent comes online. My favorite is Klein, but the Cursor is probably the most famous. And then Windsurf is very similar. And then you have ones that work. So these work in the VS Code, Visual Studio Code IDE. They work as either forks of that or extensions within it. So I'm going to talk about Klein, which is an extension. But it works very, very similarly to Cursor and Windsurf. And I can talk about the nuanced differences between these, but for our intents and purposes, just for an intro, we'll just gloss over that. And then there are command line based tools like Aider was really the first really popular one. Claude Code, I think they call it, is very similar to Aider, but it's like it's Anthropic's agent tool, but it works entirely in the command line. So if you're comfortable working in the command line, this is a great option. If you prefer the IDE, then you might want to work with one of these IDE first agents, or there's like an extension in Visual Studio Code that allows you to interface with Claude Code. All of these tools are being rapidly developed. Every week it changes, but anyway, there's lots of versions of this. But notably, these tools are separate from the LLMs themselves. And most of these tools can be run with any LLM. So they're really two separate threads of development, though a lot of the LLM companies have started to make these agent tools specifically tailored to their LLMs. So it's kind of converging, but actually I like the idea of them being separate because I think they're really two separate things and they work together better.
Yeah, sorry, but kind of a side but related question. So you mentioned these are basically doing text prediction. I wanted to go a little bit deeper into that and understand as these tools are getting more and more complex and getting specialized into tasks. The fundamental concept that these are just trying to predict the next word and that the loss function is predict the next word and kind of iterate.
Right. Let me get you this is a long question. You need a mic.
No, I'm trying to understand a little bit better what these things are doing or are trained to do, because as they're getting more and more complex and more task specific, is it still correct to think of it as they're trained to predict just the next word and kind of iterate on these? As they produce text, then that's kind of the input they get to predict the next word and the next word? Or is there something that is changing and some new ways in which they're doing that? Is it still kind of up to date to think of LLMs that way?
I mean, I would say yes and no. So I think it's always good to keep in the back of your mind that all these models are really doing is predicting the next token. Next word.
Not word, sorry.
Yeah. Whatever. Word is close enough, like for the intuition, right? And that's important because it really helps you understand what kind of biases they might have, right? How training data could influence it and what the limitations might be. On the other hand, it turns out, I would never have predicted this, but it turns out that like the better the model is at predicting the next token, it requires it to really represent information internally to the point where it's just representing more and more and more information, more and more relationships, to the point where it's actually very good at solving problems. Mm-hmm. So it turns out that in order to predict the next token effectively, you actually need to have some at least functional knowledge, whether it's like knowledge in the true sense is kind of philosophical, but at least it's functional knowledge of the subject matter, right? To answer questions, but even to do development. Like you'll see, it behaves in a way that it's almost incredible that all it's doing is predicting the next token. But still, understanding like, here, I'll give you an example of why it's important to keep that in the back of your mind, because they have this problem of hallucination, which I'm sure you all have heard about, right? Where if you ask it for citations, sometimes it will give you correct citations, real papers that happened, but often it will give you incorrect citations. But the weird thing is these incorrect citations, they are good enough to fool experts, because often they will mention authors who are prominent in that field and years when that author was in their prime, but they just never happened to publish that paper at that time. It just never happened to happen, but it could have happened, right? Like, and even an expert would say, oh yeah, that's, it's monkey reaching, that's Georgopoulos at this year, that's like makes perfect sense that would have happened, but there is no Georgopoulos paper that year, right? So, so you have to be very careful, because it's doing that through text prediction, right? And that's the kind of error that you can make when all you're doing is text prediction and not like necessarily looking up sources. But that's where the tooling comes in, right? Because that type of problem, that hallucination of citations, is a very easy problem to solve if you have a corpus of actual citations and you tell the LLM only include citations that you can find in this list, and it's able to follow those instructions, then you can solve it with tooling, right? So that's why the tooling is so important, is that it's kind of filling the gaps that are created by the fact that all you're really doing is token prediction.
Okay. Yep. Thanks.
Okay, so how do agents work? Can you guys see this? Do I need to turn the lights off? You can see it kind of? All right, I'll talk you through it. So you start your task, and first thing you do, this is like the Klein workflow. All the other workflows are very similar. The first thing you do is you use Git to create a checkpoint, so that if your agent goes off on some weird tangent, you can revert back to that point in time. Then you get the environment details. So this includes the system prompt, which here is about 13,000 tokens. So it's a substantial number of tokens. And this is instructions to the agent. It's saying, here are the tools available to you. Like, it's saying, you are a software development agent. This is your job. You're going to edit files to accomplish the task that's given to you by the user. Here are the tools available to you. You can edit files, you can read files, you can replace certain things, you can do search operations, basically telling it how to perform the actions of a software developer in code, right? Like, here are the functions available to you that are basically the functions that are required to write software. And then the user has the ability to give custom instructions, and also it will have information about the state of your IDE, so what windows are open, because it's going to preferentially try to work with the windows that are open, assuming that that's probably what the developer wants it to do. Okay, so it has this, and then it has the conversation history. So as you're having this conversation, it's going to gather information about your project, about your intent, about things that it's tried, and all of that gets put into context. So if you're thinking about this text prediction thing, the message that you send it is this tiny little thing at the end, and then all the rest of this text that's being sent up to the LLM is the context of the conversation and the tools available to it, and all of this other stuff. It's thousands of words of other things, right? So it's about the system prompt, and it's about the custom instructions, and it's about the previous conversation. And at the very end, you've got like what the next step is, what you want to do now. Okay, then you send this up to an LLM. And here are just some examples of the most popular LLMs to use for this. Claude has been my favorite so far. It's really good at following instructions and understanding how to use functions. It's trained specifically to be good at function calling and like get that syntax right. So it tends to not get lost in the instructions. So it goes up, and then the LLM outputs something, which is a tool use. Everything it outputs is some decision about what tool to use, it was told about these tools in the environment details and in the conversation history. So it can do things like execute a command on the terminal, and it will ask you to approve it if it's like a destructive command, or a potentially destructive command. So if it's creating a file, it likely won't ask you, but if it is trying to delete a file, it will require user permission. You can replace a file, you can search, read, list files, write to a file, things like that. Also, you can use MCPs. So this allows you to add any custom tools that you want to the capabilities of the agent. So we can decide, oh, I don't want to do any of the default actions. Actually, I want to do something that the user provided. And there are now hundreds of different MCPs that can provide different tools to the LLM. And it's actually quite easy to make these custom tools. And I'll show you some examples of that. Or it can attempt completion, which means tell the user, hey, I'm done, and write a summary of what it did. Right? So those are the options. And then that exits the loop. But if you don't do attempt completion, then the next thing it does is goes right back into this loop. Recursively makes client request, and it just continues and continues and continues until it decides that it completed the task. Okay. Any questions about that? We're about to see a demo, so maybe it will make sense after the demo. Okay, so here's how I set this up. I'm not going to wait for everyone to set this up right now. If you're interested in doing this, I'm happy to work with people after this to help you get this set up on your own computer and help you make decisions about maybe what model to use if you are a little more cost conscious. But I'm going to show you basically how we use this in our group, like now basically every day. And yeah, by the way, these slides are already on the slides folder. So if you want to check this out yourself, that's the best way to do that. Okay, so the first thing is set up an API on OpenRouter. So OpenRouter, let me just go there really quick to show you. It's a website that allows you to make calls to basically any LLM. So it aggregates over all of the companies and all the open source stuff. So there's actually just tons and tons of LLMs, most of which you probably would never want to use because they're kind of experimental. But it has some of the featured models here. You can view trending. It's probably a good place to figure out where the really interesting ones are. And so one really nice thing about this is that since it's kind of a hub for using these tools, it can aggregate information about what models are the most used and what tools are using these models. So Klein is just barely in the lead over RuCode, which is a fork of Klein. So there's RuCode and Kilo Code, which are both forks of Klein. They're like, Klein is open source and anyone can make a copy of it. So 2 or 3 times now, groups have made their own version and then went off on their own direction, developing the features that they wanted. So Klein is still the most popular, but only by a slim margin. The forks have started to catch up. But even within Klein, you can see what are the models that are most commonly used. And you can see here, Claude 4 is the number 1, and then Claude 3.7 is the number 2. So you can see there's a big preference towards using Claude, and I've found that Claude has been the best in terms of coding. And then close behind is Gemini 2.5, and then you get to some other models as well, which are also quite good. So the way you would set this up is you'd go over here and you would add credits, and then you would add a key. So credits you put in, you can buy credits using a credit card, and then you generate a key here. And you can set this whole thing up in about 5 minutes. Once you have a key, you'd go over to Visual Studio Code. Now, the way you would, I was just doing stuff there. Let me get to NWB Inspector, which is what we're going to use here as a demo. So the way you would install this, so first of all, if you're not familiar with Visual Studio Code, this is an IDE, interactive development environment. If you're a MATLAB coder, then you know the MATLAB IDE. It's very similar to that. I know a lot of you are doing coding in Jupyter notebooks, so maybe you're not as familiar with using VS Code, but this has some nice integration. If you want to do like multiple file things, if you want to create libraries, use Git integration, that kind of thing, this is like a nice app for that. And
It's really good with Jupyter notebooks as well.
yeah, that's exactly. The way I like to do it is I'll do experimental stuff, visualizations in the notebook. Once I have something I like, I'll move it over to VS Code. I think that's a pretty common. Oh, true. You can run them in there as well. Oh, you like that more? Okay. Yeah. It can. You can run notebooks in VS Code. That's nice too. Okay. So the way you would get Klein set up, and it's free, is you go over here to extensions and you can just type Klein, and it's this one. And you would just have the ability to install. I already have it installed, but you would just click install here. And then once you do that, you'll have this icon show up. I'm going to exit this out. And you would want to set this up. So the way you would do that is you'd go here. You would click API provider, open router. You'd paste in your API key. And then I would recommend starting with Claude Sonnet 4. It's a bit more expensive, but it will show you the capabilities. If you're really cost conscious, there's a brand new model called Kimi 2. Kimi, I think it's K2 here. Yeah, Moonshot Kimi K2, which I've been using a bit, and it's pretty good. I would say it's not quite as good as Claude, but it's very good. Okay, so that's the setup. I'm gonna move over back to Claude Sonnet. Okay.
I cannot miss. What's the cost on average for?
You'll see. What the demo I'm about to do is going to be probably like 20 cents.
Okay.
Yeah. But there's a cost counter, so you'll see it.
Oh, okay.
Yeah. Okay. So let me just delete this. All right. Now, it has this wonderful ability to get context from a website. So I'm going to show you an issue, NWB Inspector. So this is the tool that we use to inspect NWB files before they're uploaded to Dandy. We basically have a collection of dozens of like heuristics that help make sure that there's no incorrect information or that there aren't like misleading pieces of information in the NWB files. To the extent that we're able to automate that, we do it within NWB Inspector. So we have just dozens of checks for all sorts of different things to make sure that, for instance, if you have timestamps and data, that they have the same length, that kind of thing. And let me look at these issues. There was one. Okay. Here's an issue that I like to show as a demo because it's fairly straightforward. We were getting, sometimes people were uploading data where the subject ID or the session ID had a slash character in it. So that's fine, NWB doesn't mind, but when you put it on Dandy, they use the subject and session IDs to generate the file names. So now all of a sudden those file names have slashes in them, which then mangles the path. So if you're gonna upload it to Dandy, you don't wanna have these slashes in your subject or session ID. So we wanted to create a check to make sure that any NWB file that's going to be uploaded to Dandy doesn't contain these IDs that have slashes, okay? Straightforward. So what I'm going to do is I'm just going to copy this URL, and I'm going to go over to Klein here, and I'm going to say fix at this URL. And I will turn off auto approve so you can actually see what's going on. So first, it reads this and it summarizes the issue. The issue is asking for a feature to add checks that ensure slash characters are not present in session ID and subject ID fields. So it correctly understood the issue. First, it wants to view the source here. So, okay, I'll say sure. It was able to correctly identify that the check should be in this NWB file metadata check. So it's going to read that file. So all of this, each of these things is a loop, right, in the agent. It wants to look at how things are imported, okay. Okay, so here's a kind of wrinkle. This is interesting. So I've done this demo many times, and there's actually a PR here to fix the issue. So it found this, and it's saying, oh, I want to look for the branch where this was already implemented. So it's a little too smart right now. So what I'm going to say is, this is a demo. Ignore the existing PR and branch that fixes this issue and fix it yourself. I'm going to reject it with this message. I understand. I'll implement the fix myself. Okay. So it's just reading, as a developer might, as a new developer might, it's reading all of the code in the library, understanding where it needs to go. Looking at the tests to understand the testing pattern. Okay, now it's got a plan. And it's automatically writing in here the checks it needs to write. All right, now let's look at what it wrote. It does a register check, which is correct. I mean, obviously you guys aren't that familiar with this library, but these are pretty simple checks. It's saying if the session ID exists and there is a slash in the session ID, produce an inspector message that tells the user that they can't put a slash there. And then do the same for subject ID. These are correct. So I will say save. It's complaining about Pylant's syntax errors. I'm going to say ignore those. So you can see here, oh, actually, no. It's talking about the type checking an existing code already. Now I need to update. Oh, it's saying the Pylant's errors are expected since they're related to type checking and the existing code already has these patterns. Now I need to update. Oh, actually, it's correct. It's recognizing that it needs to import the functions that it just wrote. Let me make this a bit bigger so you can. Oh, that's too big. All right. Forget that. Sorry. Hope you can see it. It's correctly imported. It's recognizing, oh, actually, it also needs to go in the all list, so it's doing that. So here's the tally. We're up to 28 cents. You can set this to auto-approve, in which case it just flies through, but that's a little dangerous. Sometimes I do like to do that, and then I'll just look at the changed code in the, like in this window. You can see all the files that have changed, but that's kind of advanced. You have to really trust it. Okay, so now it is editing the tests. So it's importing these functions in the tests, which is correct. Now it needs to implement those tests. I like to do one test where the check passes and one test where the check fails, at least those four. So let's see if it implements all four of those. Test check session ID slash is pass. Good. Test check session ID slash is pass none. Okay, good. Test check session ID slash is fail. Good. It tests that this will actually throw an error. Session ID slashes. Okay, good. Subject ID pass, subject ID pass, subject ID fail. Good. This is correct. Now it's running the tests. They passed. But it only ran one of the tests. So now it's, let me run a few more tests. Okay. It's running the tests one at a time, which is a strange choice, but okay.
Yeah, it's a business decision.
Maybe. Oh yeah, we're up to 50 cents. They're really squeezing me. Yeah.
I mean, if one test doesn't pass, it isn't worth doing the others.
That's true. Yeah, it's saving on compute, but I'd rather it save on API calls, but that's okay.
Yeah.
But you're not paying Klein, right? So Klein has no.
Right. But it's the LLM that's making the decision.
Oh, it's the LLM.
I don't think it's acting nefariously. It's never. Sometimes it does weird things, slightly weird things, like idiosyncrasies. I've never seen it run one test at a time before. Right. Also, let me check that the tests work with the registration system. Yeah. Okay. Perfect. All right. Now it's running more tests. That's all the tests in that file. Okay. This actually would be really helpful if you had a library where the tests took a long time, right? So, okay, it's writing a demo. Sometimes it kind of goes, this is a good example of one of the weaknesses of Claude. It's like, you tell it to do ABC, and then it does ABC, and then D, E, F. Like it just keeps on going. And you have to be like, no, you did it. You're done. I don't need, a demo. Oh, yeah, you're right. That's probably why. All right. It's going to keep, I think it's because I told it was a demo, it's going to keep on doing stuff. But it did complete the task. So, and it ran the tests. I mean, and we can run all right, stop. We can just run PyTest ourselves. So this is like demonstrating how it's doing most of the work. It did all the coding, but then the decision-making process, it's like kind of 50-50, right? Like I kind of need to steer it a little bit. It's just going to keep on going, doing random stuff. It's like it already completed the task. So like stop, you know? But yeah, this is going to work. Now you can give it the capability through MCPs to create a pull request on your behalf. I tried that out. It did work, and then I became uncomfortable with that. I was like, that's a line I don't really want to cross. Like, I want to be responsible for the communication of any code that I'm responsible for. I want to be able to review it before it gets up as a pull request, and I think that's probably a good policy. Because, I mean, for myself and for anyone on my team, you're responsible for the code that you submit as pull requests, even if an AI wrote it. Like, you can't just be like, oh yeah, an AI wrote it. That's not an excuse. Like, it's your problem. But you can look through here and see it correctly accomplished this task. So, and it involved reading multiple files, editing multiple files. And it didn't actually, it anticipated this import error. Most of the time when I have it do this task, it doesn't anticipate that error. It runs the tests fail. It's able to look at the traceback and then correct it and understand that the error is due to an import error and then correct it. So that's actually a more common workflow, is that it is able to interpret traceback errors and fix them on your behalf without any intervention. Okay. What is going on? Oh, right, it's a screenshot. Okay, the next generation of this, which has already been released, is where you have an issue on GitHub and you assign it to an AI. And this has already been implemented with Copilot, where I can take any of our issues on GitHub, and instead of assigning someone on the team, I can assign Copilot, which will then automatically spin up a virtual environment, clone the repo, install it, and start working on it. And then maybe like half an hour, 45 minutes later, you'll get a PR issued by Copilot trying to solve this. So let me see if I can show you an example of this. Pull requests, closed. There we go, issued by Copilot. So, all right, so the issue here, let's see, it's fix this. So we wanted a how-to for converting bespoke video file formats to MP4 with FFmpeg. And we thought, hey, let's just assign Copilot and see what happens. 45 minutes later, we get this PR, which is a great tutorial on how to do that. You can interact with the AI just by leaving comments on this PR. So Paul Atkinson, who's a member of my team, he's like been really leading the investigation of this approach, and he's gave feedback to Copilot as if it were a peer. And then every time you leave feedback, it will go and try to incorporate that feedback and iterate a few times. And then eventually you approve and merge it, just as if you're working with a peer. Now, this approach, I would say I'm a little more hesitant. I think like if you're trying to create a tutorial or something like that, it might be okay. You have to be very careful about reviewing this code because it's much more hands-off. Right? At least when you're doing it as a client extension, you're reviewing each decision it makes, and you have the ability to interject with each decision it makes. Here, it's kind of giving the AI even more responsibility, and so you just have to be more careful. And we're kind of trying to decide whether we really want to embrace this level of automation. Okay, so AI can code. I hope now I've convinced you AI can code. The question then is, how much does it know about neuroscience? So there's this really interesting paper where they produced a platform called Brain GPT. And what they did is they created this benchmark where they could determine how much functional neuroscience knowledge these LLMs have. And the way they did that is they took abstracts of new papers and they took one word out. So they took out the word increase or decrease, and then they replaced it with bracket increase / decrease, right? They made it so they chose words that could have gone either way in the abstract, but it was like one of the main findings of the paper. And they took out that word, and then they asked the AI, okay, which word was it, increase or decrease? Now, they intentionally chose papers that were released after the training window of these AIs, so they didn't have, the LLMs did not have an opportunity to incorporate this information into their training set. So the only way they could get a good answer here is if they were to apply knowledge of neuroscience, abstract knowledge of neuroscience that they were able to gain through the corpus of text that they were trained on, and apply that to this paper to see if they could predict the answer. So they also did this with expert neuroscientists. They did it with research scientists, postdocs, faculty, pre-doctoral students, postdoctoral students. Now, across the board and across domain, they did behavioral, developmental, cellular, neurophysiology disease. Across the board, they got about 60%. And interestingly, at every career stage, the more senior testers didn't perform any better than the junior. They were all about 60%. So 60% is it's above chance, but it's not that far above chance, right? Because 50% would be chance. And then they asked the AIs, and the AIs all scored about 80%. Now, this is old. Llama 2 is old at this point. It's ancient, okay? So these models, first of all, they chose open source models because other things they did in the paper required open source models. And also, these are really old open source models. This is when we were really starting to understand the capabilities of LLMs. I haven't seen the stats on what OpenAI 03 high would be, but I would expect that it would be much higher than 80%, could be 90%. Okay, so clearly, for me, this was an awakening moment, right? It's they have an ability to synthesize information that exceeds your average neuroscientist. So how do we actually use this? The thing about this is wow, it's shocking and it's really impressive and interesting, but this itself is not that useful, right? It's not a tool, right? It's simply a demonstration of capabilities, but how do you actually leverage this to accelerate research? So this is what I've been working on. So it can code, and it knows about neuroscience. So the question is, can it do neuroscience data analysis? So I've been doing this as a building upon Klein, which allows me to use this kind of semi-supervised approach where I kind of steer it in the right direction, just like you saw I did before. And I've been using mostly Claude Sonnet 4 because it's just been the easiest to work with. And now, in collaboration with Jeremy, actually, these tools, many of them were developed by Jeremy or in collaboration with Jeremy. He created this NeuroSift-based MCP that exposes many of the functionalities that you're using to search these data sets, exposing them to the LLM. So it can do a dandy search, either a lexical search or a semantic search, just like you do in the interface. It can print out information about dandy set. It can list assets. It can analyze a plot. It can print out information about the specific NWB file. So I'll show you the exact capabilities in a second in the demo, but what we want to answer here is a bunch of different questions that are kind of implicit in this, right? For a given finding, are there any dandy sets that could reproduce it? How many? Are they sufficiently annotated to actually use them? Can an agent find these data sets? Are there any false positives? Can the agent access the data and load in relevant data streams? Can it write a reasonable analysis? Can it produce reasonable figures and stats? Can it understand those figures and or stats it produces to answer a question, a scientific question? Okay, so then you have questions that roughly follow that workflow. Okay, so here's the first thing I tried. I wanted to do a proof of concept of direction tuning. So identify a data set that contains center outreaching trials and extracellular electrophysiology data and use it to demonstrate directional tuning of M1 neurons. And then I gave it really kind of specific instructions. So I basically was trying to think like, if I were teaching a course on systems neuroscience and I wanted it as like a really complex homework assignment or maybe like a final project, like how would I word it, right? And to see if I could kind of treat the LLM as if it were my student. Calculate direction tuning index for each cell based on firing rate and the direction of reaching trials. For the 4 most selective cells, show 1, a raster plot where the trials are grouped and colored for each direction, and 2, a histogram aggregating over trials in the same reach direction. Once you create the plots, load them and view them using the MCP for reading images to ensure they were made correctly and fix any errors. Once the plot sufficiently demonstrates directional tuning or lack of directional tuning in this data set, finish. So slightly modified to speak MCP, but not really that modified. And also, there's a lot of implicit knowledge here, right? Like, I just used the term direction tuning index. So it has to know what that actually means. And here's the result. I had to do a slight bit of steering similar to what you just saw in the demo. I didn't write any code, but for instance, in the read image MCP for this, it tried to use the relative path and it needed to use the absolute path. And I happen to know that. So I was like, no, use the absolute path of the image. Little technical glitches. And also, the first time it plotted this, these were overlaid on top of these. So I said, well, separate those. So, okay, so it was a little bit of steering. But besides that, it wrote all of the code. This happened in 10 minutes and took about $2 worth of credits. And here you have, if you haven't seen that many directional tuning plots, essentially what you have here is this is the time of a trial. So this is the start of a reach, the 0 point. These dots represent the spiking activity of a single neuron. So this is 1 neuron. And the colors represent the reach direction. So you can see here that reaches in the 0 degree direction have a low firing rate, and reaches in the 90 degree direction have a high firing rate, and then there's kind of a graded response in between. And then interestingly, across these 4 neurons, they have tuning for different directions. So this 1 shows that individual neurons have tuning for reach direction, and 2, that different neurons have different tuning. So this, I would say, passes the test. It shows reach direction tuning. I would say, though, a caveat, this is another run. And there are some things I like about this. It created this polar plot, which I didn't tell it to do. So I think that's a really cool way of visualizing this data. However, these results are junk. I actually think this was an issue with the data set or maybe with the session. So it lacks the ability to judge when it needs to backtrack multiple steps. Right, so it got all the way to the results, and then a really good system would say, these results are junk, let me try another session or another data set. It didn't do that. It was just like, here you go, here are the results. So I would say maybe, I don't know, B-. It did more or less what it was supposed to do, but it could be better. But the results here are quite variable. So sometimes it does a stellar job and sometimes not so much. So I was thinking, okay, that was reach direction. It was able to do that. What are some fundamental findings that you should be able to reproduce in many different data sets that there's really no question at this point? It's been reproduced over and over again. We know that they exist. We know that they're true. And also, I wanted to think of findings that were foundational in the sense that many current papers rest upon that finding, right? So for instance, orientation selectivity. That's one of the oldest findings and most reproduced findings in systems neuroscience. Selection in the visual system selection, in the early visual system, edge detection essentially. But there are lots of studies now that use that either as a reference point or look at context dependence. I mean, even the IBL data set rests upon the assumption that you have visual system orientation selective tuning, right? So so that's true of all of these, like linear receptive field modeling, directional tuning and speed tuning for the motor system, frequency tuning in the auditory system. You got place cells and grid cells in the navigation system. So I was like, okay, can we reproduce these? And to be honest, I haven't gotten all the way through these, and I'm working through kind of how to create the right guardrails to enable the AI to do all of this. But I have done some of them. So here with place cells, I wanted to try an approach where I was much less specific in the things I wanted to create. I was just like demonstrate place fields using the Dandy archive. Start with analysis of a single neuron. And then I was trying to give it more instruction about how I wanted it to do it. So for each computational step, use statistics or a figure to ensure the output is what you expect, and then proceed. And this is what it came up with. And actually, this, I think, is really telling. So here, it found a data set and was able to compute spatial selectivity. And here's 2 neurons, which shows in the gray, it shows the position of the animal, and the red dots are the firing rate of neuron 1 or neuron 5 and neuron 10. And it on its own calculated sparsity metrics and information metrics, bits per spike, which is interesting. And from what I can tell, it did this correctly. And it shows that there's different selectivity here. And I think this summary, which, by the way, it produced on its own without any prompting, this is really impressive. So analysis of spatial firing patterns into hippocampal neurons revealed distinct types of spatial selectivity. Unit 5 exhibited multiple scattered firing fields, and then some stats. Unit 10 demonstrated more focused firing patterns. And then this final paragraph, I think, is really something. Both units show spatial selectivity, but differ from classical place cells, which typically show a single, well-defined firing field. Instead, these neurons may represent different aspects of spatial information, possibly encoding boundaries, landmarks, or multiple reference points in the environment. The analysis pipeline successfully identified and characterized these spatial firing patterns, providing quantitative metrics and confirming the cell's spatial selectivity. So this, I think, is really key because it correctly pointed out, and this is something that has been a frustration of mine every time I look at hippocampal cells. It's like most of them are like this, in my opinion. Most of them don't have clean, like this is this. I mean, you can cherry pick 1 or 2 cells that do. But what was so fascinating to me is like, if you gave this assignment to a graduate student, many of them would cherry pick the cells that have a clean place field. And this didn't. This said, look, I'm going to show you 2 cells that have great spatial selectivity, but I'm going to point out that they deviate from the classical finding. And it shows that it doesn't fall prey to a very common sort of bias that you would see in novice scientists. So, also I asked it to summarize what it did, and it generated this summary. It has a function for downloading the file, a function for inspecting it, one for computing occupancy maps, one for rate maps, one for spatial information. It has a function for plotting, and that has one function that aggregates over all of these. This architecture is, in my opinion, perfect for this analysis, for like this assignment. So it was all organized in the perfect collection of functions. I can also show receptive fields in V1. I was able to reproduce that as well. Next steps, try this across different ones. Try providing reference material. I'm really interested in collaborating with you, Guillaume, to see if we can integrate Pineapple and get these to be even more streamlined. Formalize an evaluation process for the results that they produce. And also ask it, what are the next steps of analysis that you would recommend? And also, should we move away from Klein? Klein is great in some aspects, but kind of locks you to a certain workflow. It makes it really difficult to, for instance, launch 10 or 100 of these at the same time. So Jeremy, in response to this restriction, created Mini Klein, which has all the capabilities of Klein, but isn't locked to VS Code. And it's actually able to work much more efficiently because it doesn't require nearly as much of that initial context, which tells Klein how to operate with VS Code. It doesn't need to know that anymore. So that is able to more or less reproduce these same findings. But you don't have the ability to steer it. So those are the trade-offs. And right now, it seems like we kind of do need to do at least a little bit of steering to get this to work. OK, now I want to show you a demo of what this looks like, because I know this sounds a little crazy. All right. I was just experimenting with stuff, so I'm just going to delete this. Okay, I'm not going to show you the whole thing because it could take a little while, but I will show you there's this Klein rules file, which is automatically read. And this gives it some guidance I've kind of been accumulating these guidances based on like errors that I'm seeing in the script. So it tells it to search the archive, create a dedicated analysis folder, use certain tools to learn about the NWB file, start with a single neuron and then progress, things like that. Use progress bars if you're going to do something that's going to take a long time, etc. And I'll show you the tools that we made available to it. So go to installed MCPs, these NeuroSift tools that Jeremy put together. So these are functions that are added into that agentic loop as options, right? So it can do Dandy search, which is classic lexical search. It can do semantic search. It can get info about a Dandy set, info about the assets of a particular Dandy set, info about a specific file. It can also search OpenNeuro, which we won't be using, but it can do that too. And yeah, lots of functions like this. Those are the main ones that I'll be using. Okay, so let's try it out. Fingers crossed. All right, I'm just going to start with nothing. So there's nothing in this repo except for the client files. I'm just going to say demonstrate place fields. All right. The first thing it says, okay, because it read my instructions, it knows that it needs to search the ND archive for this, and it's using the NeuroSift tool called Dandy Search. Now, this is not going to yield any results because it's too specific. So it's going to take that information, it's going to think about it, and it's going to use the semantic search instead, which is the right approach. And now it has a bunch of results. Let me just X this out. Oh, that's not what I wanted to do. Okay. I can minimize it. There we go. So it returned a JSON response of the top matches for the semantic search, which are good results. So transformation of spatial map across the hippocampal lateral septal circuit. That sounds good. Large-scale recordings of head direction cells in mouse. Yeah, okay, I mean, all of these are really solid. Now it picked one of those, and it wants to understand more information about it. So it's going to use this tool, get a response. And now it understands it gets the full description and gets information about what neurodata types are in there. And it says, yeah, that sounds good. I'm going to look at what Dandy sets are in there, or what NWB files are in there. Okay, great. It found it. It's going to pick one of those, get information about it, understand really the contents of that NWB file. And it says, all right, this is good. I can work with this. I'm going to create an analysis folder and start writing code. First, it creates a README of a plan. And then it starts writing. Loading data. It's streaming data in using Lindy. It's extracting the position data from the wheel. It's extracting the spike data. It's getting trial information, processing the position. Normally, I would read through this for the sake of the demo. Anyway, I don't think we're going to have time to go through all of this, but you get the idea. Now it's going into place field analysis and calculating the occupancy map and relating that to the firing pattern. It's basically reproducing those results that you saw on the slide earlier. And it's pretty fast. So this will, if it doesn't get stuck in a weird rut that needs my help to get out of, this will be able to reproduce those findings in about 10 minutes. All right, that's basically it. Yeah, so I'll take questions.
Yeah, I'm still a little bit shocked, but,
Yeah.
and I have probably many questions. But so a first one that I think is of general interest is you obviously played around with this a lot, and I guess you tested a lot of different prompts and did some prompt engineering. For example,
Yeah.
I noticed you setting caps do not use synthetic data for this, right?
Yeah.
So which are some general rule of thumbs or some suggestions
Yeah.
when you do prompt engineering?
Yeah,
for these tools?
so the biggest issue with Claude Sonnet specifically, it has this like obsession with completing the task, like at all costs. So if you tell it to get these tests to pass, it will attempt to change the library code in order to get the test and not modify the tests, right? It'll attempt correctly to get it to work for about 4 tries. And then it will be like, well, I could get the test to pass by simply just replacing the test with the word pass. It's like, technically, the test then passes, but obviously that's not what I want you to do, right? So you got to watch out. That was a big problem with 3.7, and they actually identified that as a problem and intentionally trained 4 to do it less, but it still does it. And so in the context of this, if it's unable to read the data, it'll just generate data. It'll just generate the synthetic. It's like, no, like try, like struggle a little bit before you just, or just tell me you can't do it, but don't create synthetic data. That's not what I want you to do. But I mean, the phrasing of demonstrate, I mean, you could imagine, okay, I'll try to do it with real data, but if I can't, I'll demonstrate it with fake data. So I just have to tell it, like, no, that's not what I want.
So these are like crazy, fiacres or unethical, like they just want to get to the result, right? No matter what,
I mean,
in
it's
a
a
way.
specific problem with this model. The others don't really do that so much. But the others get lost more. They'll like create a file, but then they'll like forget that they created it, or like then they, stuff like that. Like it requires a lot, like metaphorically, a mental model of the whole code structure in order to actually do this effectively. And Sonnet is the best at that. Like it makes poor decisions sometimes, but the decisions that it makes are internally consistent. Yeah. So good question. Yeah. So this bar here is So these are the tasks, and the colors are different types of tasks. And the bar here is your context window. So this model has a context of 200,000 tokens, and we're 60% of the way through. Here you can see how many tokens you've have gone up or down. Oh, this needs my approval because it's trying to pip install things. It's in a virtual environment, so that's fine.